Hi, I'm Bob. Welcome back to the 5 Minute Econometrics, an econometric tutorial that helps you better understand fundamental econometric concepts and estimation methods. Today, we will explore two concepts: homoskedasticity and heteroskedasticity. For a regression model, y equals beta 0 plus beta 1 times x plus mu. Mu is known as the error term or the disturbance. Homoskedasticity means the error term mu has the same variance given any value of the explanatory variable. In other words, the variance of the error term mu conditional on the explanatory variable x equals sigma squared, where sigma is a constant and does not depend on x. Sigma squared is often called the error variance or disturbance variance. Sigma is called the standard deviation of the error. In the model, the error term mu is the random component of the observations. We can show that an equivalent definition of homoskedasticity is that the variance of the outcome variable y is a constant, sigma squared. In addition, it can be proved that the homoskedasticity assumption can also be expressed in an unconditional form. If the variance of the error term mu depends on the explanatory variable x, then the error term mu is said to exhibit heteroskedasticity or non-constant variance. Similarly, an equivalent definition of heteroskedasticity is that the variance of the outcome variable y depends on the explanatory variable x. Homoskedasticity is an assumption in the linear regression models. However, keep in mind that the homoskedasticity assumption is not needed for the OLS estimators to be unbiased. As long as the zero conditional mean assumption is satisfied, the OLS estimates are unbiased or consistent, no matter whether the variance of the error term is homoskedastic or heteroskedastic. The variance of a variable measures how spread out the distribution of the variable. We use the variance of the error term to define whether the model is homoskedasticity or heteroskedasticity. We can see the spreads of distributions of observations in a graph. By visualizing the distribution of observations, we can analyze patterns in the data. For example, when plotting hourly wages against years of schooling, we observe that the variance of hourly wages increases as years of schooling rise. Among individuals with more years of education, wages fluctuate more widely compared to those with fewer years of schooling. In other words, the variance of the outcome variable, hourly wage, depends on the explanatory variable, years of schooling. This indicates that the model suffers from heteroskedasticity. Constant variance is one of the classical linear regression assumptions because it can lead to the efficiency of the OLS estimators. With the homoskedasticity assumption, along with the other 4 classical assumptions: linear in parameters, random sampling, no perfect collinearity, and zero conditional mean. The OLS estimators have smallest variance among all linear unbiased estimators. The residuals are unbiased estimates for the error terms. We can use the residual sum of squares, SSR, to estimate the variance of the error terms. I will illustrate the difference between the error term and the residual in the next topic. Here, we will use the formula for the unbiased estimators of the error variance. Sigma squared hat is an unbiased estimate for sigma squared. It equals the residual sum of squares divided by the degrees of freedom, n-2, for a regression with one explanatory variable. In Stata, the result window shows the residual sum of squares, SSR, the degrees of freedom, and the estimator of the error variance, sigma square hat. For example, after regressing hourly wage on years of schooling, we obtain this result. The residual sum of squares, SSR, equals 677,888. The degrees of freedom equals 4,162 because the number of observations is 4,164, and there is one intercept and one explanatory variable in the model. The error variance estimate is about 163. The reason we estimate the error variance is that it will be used to calculate the variance of the OLS estimators, beta 0 hat and beta 1 hat. We should be aware that the calculation is based on the assumption that the model does not suffer from heteroskedasticity. But we know this is not true from the graph we just plotted. One straightforward solution is to use the robust option for heteroskedasticity. The significance of the estimates does not change. In today's topic, we have discussed homoskedasticity and heteroskedasticity. That is, whether the error term of the model has a constant variance or varies with explanatory variables. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.